So good morning. Welcome to Krishna's classroom. We continue with our discussion on the inner product spaces. Essentially, our objective is to introduce the concepts of length for a vector and angle between two vectors, and the experience that we have gained by looking at the geometry of R2 or R3 and trivially on R is to be generalized in a more general setting, and we have completely explored this on R3. And more generally, I think we can now write down what Rn is. So Rn, you take Rn, then Rn over R is a vector space of dimension n. All these things we follow from now on discussion in linear algebra. R is the associated field that we are taking, and then let us denote a typical element x by and y that is defined by eta n, where psi i's and eta i's are real numbers. And then we have defined addition eta n alpha belongs to R. Now this endows a collection of objects in Rn with a linear space structure, and we now introduce the so-called inner product on this space. So the inner product, we have already used this notation. The inner product is a map from with a certain set of properties. So the natural inner product that you take here is this x, y, you define it as, this is the inner product, it is defined as sigma eta j. Then you can show that the following properties hold. The first property is that it's a real valued function, so this condition is automatically satisfied. The first property is that in other words, what you observe is that the ordered pair xy, the inner product of the ordered, the inner product associated with the ordered pair xy is the same as the inner product associated with yx. So we call this symmetry. Symmetric. The second property is that alpha x or I will put it this way, combine both and then write. So what I want to do is this. Alpha x beta y set. Now these are the properties of the whatever we have defined here. You can verify where alpha beta x y now the third property, that means it is linear with respect to the first variable. Now from this it will follow that it is also linear with respect to the second variable. Okay, so you can show that. The second variable. That is very easy to verify. And that means inner product of x with alpha y plus beta z is equal to inner product of x alpha times inner product of x with y plus beta times inner product of x with z. So that can be easily verified because you will have to make use of this. So systematically try to work it out. The third part, the third property that you have is that greater than or equal to 0, and if you want you can mark it as a fourth property. All these properties you can verify in this case. Okay, right? And we shall also introduce the notation norm of x. You define it as the inner product of x with x to the power half. That is well defined as a real number. And this is what you call the length or norm and you see that it has all the properties of the length. that you have. Now this is the generalization from our experience on working with R, R2 and R3. Now what we do, we can possibly generalize this to the following. So this is what we expect. Let X be a inner A be a linear space over R of dimension that is assumption. That means it has a basis consisting of n vectors, okay, spanned by n linearly independent vectors over R. Now the same four properties can be written out. Now we write, instead of writing for xy belonging to Rn, we write the following. So we have so x plus y and alpha x are given. Now we define a map R having the following properties. Because there is a question that comes. The properties are, the first property, that two, that is the image of the ordered pair xy is the same as the image of the ordered pair yx. The second property is the linearity. So you have alpha x plus that is, it is linear in the first variable, and consequently one can prove that it is also linear in the second variable. So one can prove the following, that is 2 prime x alpha x Now 2 prime is a consequence of one and Can prove this. Then we have the third property, namely and probably the fourth property, if and only if suppose you have such a function defined from x cross x to R, then this we call the inner product. Defines an inner product on X. And consequently, so X is called an inner product space. Of course, immediately a question comes. Suppose you take an abstract n-dimensional real vector space in the sense that the associated field is real. Does there exist such a function from x cross x to R? Okay. So one of the immediate questions that you ask is this. Does there exist a function with the above properties? We have seen that in R and it does there exists such a function. So it's quite easy to see that there exists not just one function, there are several such functions possible. So let us quickly examine this problem. Let be an ordered basis for this. I mean, there are several such bases possible. Choose any one of them. Then X is uniquely represented by well, psi 1, psi 2, psi n are, so psi j they are uniquely determined. And now define theta. Now this defines this endows X and inner product and you see that all these properties are valid. So that gives an inner product. Once you verify that, it's quite easy to verify. Okay. X can be made to an inner product space. That means we are introducing two things at one stroke, namely the concept of an angle between vectors and the length of a vector. So some geometry is, apart from the linear space structure, now we are also introducing some quantifiers into the space, namely what you would like to call the measure of the angle between two vectors in terms of cosine of the angle, and that's all. In n dimension you cannot draw the picture, you cannot really have the conventional notion of what you call the angle between two vectors, and also the notion of what is called the length of a vector, because we don't have a pictorial view of the whole thing. Okay, so it checks with whatever we had been doing for R2 or R3. Right. Essentially, what is that is happening here? Let us examine this to some extent. See, you have got X here. Now, once you introduce a basis, suppose you choose x1, x2, etc., xn as an ordered basis, then what you are doing is that you are introducing an isomorphism of x to R. So the phi is an isomorphism of x to Rn by defining phi of x equal to psi n whenever x is equal to verified all this. Therefore, now you are comfortable in a comfortable zone of Rn. In Rn, we have already introduced a inner product, and that is accepted as the inner product, or that induces the inner product on X. Okay, so this is the process. So when you have a element X gets mapped to psi I and another Y or psi j beta j, this I we soon will be reserving it for some other purpose. Now you see that we come to the comfort zone where you can more or less everything is clear. It's a very concrete space. There you have the inner product, and this the inner product of psi with eta. So you want to call this psi, or yeah. So the inner product of X with Y is taken as sigma psi I psi j beta j. So that's what we do. Want to make one more remark, that this also allows not just introduction of one inner product, but several possible inner products on this space. So let me just make note of that. Right from the beginning itself, I think one should be clear about it. The choice of the inner product on a finite dimensional vector space over R is not unique. That means there are several inner products that you can endow the space with. Each accordingly brings different notions of length, different notions of angle, and so on. Okay? How do you do that? This is because every choice of an ordered basis induces an isomorphism of the different isomorphism that you have. Therefore, the map X inner product Y is dependent on the choice of the isomorphism. Okay, so by choosing different isomorphism, one can define different inner products. dependent on the choice of the isomers. Or choice of orders. So corresponding to each choice you have a new inner product. Okay? One can define several so that's an important thing. The choice of the inner product on X over R is not unique. Okay, so that we have seen. Therefore, there are several ways in which a finite dimensional non-linear space can be transformed or can be endowed with an inner product. Okay, so accordingly, the geometry also would change. Okay, so this is introducing an additional structure on the vector space. Okay. Therefore, now that is pretty clear what goes on. Now let us see, we also made a remark. So now we look at we said that we would like to restrict the choice of the associated field to R and C. So far we have been working with R. Now recall the following. So we'll look at, see, C over C is a one-dimensional vector space. It's a complex vector space. Whereas C over R is a two-dimensional and it becomes infinite dimensional once you choose, instead of R, suppose you choose Q, then it becomes an infinite dimensional vector space. This we have seen right in the beginning. So therefore, the choice of the field has a very definite role in determining the linear space structure of the same object. So analogous statements can be made that Cn over C is an n-dimensional vector space. Cn over R is a 2n-dimensional vector space. All these are straightened. So let us see how we should introduce the inner product space. So what we try to do is we just mimic what we have been doing. Okay, let's try. Okay. The first thing that you do in these circumstances is just to mimic, try to see whatever definition we have introduced is going to stay, and if that doesn't work, you go to modify it in a meaningful way. So you take Z belonging to C. Now Okay. So Z, or we'll simply write X belonging to C. Don't take this is the real part of the vector. And Y belonging to C. Then both X and Y are complex numbers. Now define, let us define. This is our immediate instinct to write this. Okay, fine. Now let us check each one of these properties. Now you see that this is all right. It is linear so the second property of that we have looked at also holds. But coming to the third property, what is the third property? X. Is it true? Does it hold? It doesn't work. Okay? Because XX is square. And let us take X equal to I. Then what happens? Equal to I square, which is equal to -1, and that is not positive definite. Okay, therefore you see that as it is, our definition does not go through. So we have to think about a credible way in which we modify it. We would prefer, because you know that this actually corresponds to what is called the length of the vector. So we want this to be positive for non-zero vectors. So how to modify this such that this property is taken care of? Because this is something having some kind of sanctity for our purpose, for the geometry that we want to introduce. Therefore, let us modify. And let us define. You see that if you write inner product of x with x as x times x conjugate, then it becomes positive. So that's one thing that you try, and so you define this. Now you see the third and fourth conditions hold. Okay, right? The third and fourth conditions hold. But our symmetry condition will not be true, so you will have to modify it. Okay, so you see that when we try to fix the third and fourth condition, the first and second conditions do not hold. Okay, so okay, we'll change it. What is that? It's not. This is at the stage where we are introducing it, and we can think of a viable option in this regard. what we observe is this: if this condition is introduced, then what happens? So we will accordingly change the definition of the inner product. If that is something workable. So let us do that. We observe that. Now we observe that if I write x, y, y conjugate, suppose I take this as a definition, then what I see is that x, y is not equal to yx. In fact, it is the conjugate of that. Therefore, we rework the whole thing. So the first property, we will fix it. Say that then x conjugate. Okay? The second property, we observe the following. Now this is equal to, our definition would give you if you use this definition, then you will immediately see that it is alpha beta yz. So the second property appears to remain the same, but then the consequential property of these two, namely 2 prime, now turn out to be get alpha conjugate You see, this alpha and beta come outside the inner product with a conjugation. If the second term is taken as alpha y plus beta z, this you can verify. So this is the modification that turns out. So this is the modification that you have to do, and this is a consequence of this modification. So prove this. Using 1 and 2. Or 1 and 2 together implies 2 prime. Okay. So you can give a proof of that. I mean, that's quite simple. In fact, in this case you can verify, but in general this is what we would like to. Therefore, now we got some insight. Okay, whenever we generalize something, we will see that whatever we had earlier is consistent with the new definition that you have got. So what is that? See, R is a subfield of C. Therefore, we would like to see whether whatever we have been doing is valid for with R. Now you see that when x and y are real, then you see that the complex, this will give you a complex number, but the complex conjugation, because it's a real number, and therefore the complex conjugation is itself, therefore 1 implies 1. Is consistent with real field. So this is something, so our generalization is along the right path. Therefore what we do, so let complex by which you mean the associated field is the field of complex numbers. Then define the inner product on a complex value such that the following properties are old, namely x inner product y is the same as y inner product x, the complex conjugate of that. That's the first thing. The second one is it is linear with respect to the first variable. And then it is consequently conjugate linear with respect to the second variable. So the first property is conjugate. It remains the same. Or you can say that linear. That means keeping the second variable fixed, it defines a linear version. And 2 prime is this is what you call conjugate linear. In the second variable. Now this is a consequence of the conjugation that is there. And then of course the third and fourth hold. Greater than or equal to 0. And fourth property is that that you need is this. Therefore, this is the definition of inner product on a complex vector space. It's a consistent extension of the concept from a real vector space. Now you see that you can, let me just make a remark, you can conceive C as a one-dimensional vector space. Now remark, C, and we can write Z or I put it this way, X. C is a two-dimensional R. Now there you define, because this has to be real, you define as the real part of this is equal to, and you know that this is two-dimensional, so it is isomorphic to, then C is isomorphic to copy of R. And we are introducing this. So if X has is x1 plus I x2, Y is equal to that is if x is equal to where I is the complex unit number, then you are writing this as then equal to, what is the real part of this? The real part of this is x1 y1 plus y2, and this is the usual inner product on R. So this is the usual inner product on R. Okay, so that is what we observe here, right? So verify that this defines a credible inner product on the space by verifying that all those properties are satisfied. Okay. Now we possibly look at make some remarks about the names that you give. Introduce some notations or some names which we often come across. Okay. First remark, a real inner product space is called a Euclidean space. Often a complex finite dimensional inner product space sorry a unitary space. and this is called the Euclidean space. Now these are some of the terminologies that we use. Now let us introduce some examples. That I think we can conclude today's lecture from the right. Already we have seen some of these things we have already introduced. See, for Cn, so let's take Cn. Now, so psi I belonging to for j equal to now you define conjugate. This is the usual unitary space that one talks about. Okay. Now the second example, just take P. That means all complex valued polynomials with coefficients in C. Then focus xt is okay. This is the definition that we make. And this is an nth degree polynomial. If provided xn is not equal to 0, then this is an nth degree polynomial with the coefficients in C. So xi okay. Now what we define is the following. See, x and y may be of different the degree of the polynomials x and y may be different. Or what you define is the following. Show that this is a this defines that's quite easy to check. You see that x inner product with x is mod x square integral 0 to 1 dt, and then you see that this is equal to 0 if and only if the polynomial is 0, etc. So that's a direct verification. Now you see that on R2, this is to show that there is another inner product that you can possibly define. Take x to be equal to beta 2. Then define beta 2. Now you can easily rewrite this whole thing, and from this you can verify xx turns out to be simply and you can show that this is greater than or equal to 0 and equal to 0 only if this term is 0, this term is 0, which in turn says psi 2 equal to 0. Therefore, psi 1 equal to psi 2, that means psi 1 equal to 0. So, for that is all n by n matrices complex entities. We will write down a possible inner product. Yes? Okay, so let us write, suppose A is equal to A JK, it's an n by n matrix. B AJK, BJK are complex numbers. you write, define show that you can verify. Meanwhile, you also observe the following, that C is in fact isomorphic to Cn square. And what you have is this, that is in fact the trace of B star is the transpose conjugate of and this is also equal to trace of B star. Now trace of the diagonal, the sum of the diagonal elements, and this is equal to sigma So this is actually the trace of A B star that we have defined as the inner product. Okay, I think I will stop here today and then take it up in my next lecture. So thank you very much.